Today, we are going to get into the giant planets, and we'll finish it up on Thursday. But one thing that we can't avoid when talking about giant planets is this class of objects called brown dwarfs, which are, I think, my favorite kind of objects in the universe. They're very, very interesting because brown dwarfs are a broader class of bodies that are slightly bigger than Jupiter, but they're not big enough to be stars. And so I think we can learn a ton about what a giant planet is by studying brown dwarfs and really thinking about all of these bodies in a larger continuum that at one end has big stars that are crushing themselves and undergoing all of these interesting processes that generate light and heat and fuse, create new elements, some of the big elements. And then at the other end, we have smaller versions of objects that are essentially compositionally the same in that they have all the ingredients to make a star, but they don't become stars. And it's a really interesting saga that I'm going to try to unpack for you here in the next few slides. Because Jupiter looks a lot like a star, actually, in terms of its actual elemental composition, but it's not quite big enough to do the star thing. And so this is really cool because we can start to imagine different ideas for where these planets come from. Especially when we start to imagine the different capture ideas and the migration ideas as these planets form in one place and move to another. And we can develop a very rich history for our own solar system, but especially for a lot of the ones that we see forming right now. So in order to do that, we're going to make it through brown dwarfs, and then we're going to talk about Jupiter and Saturn, and hopefully we'll make it through all of that so that next time we can do the ice giants, which are an interesting twist on the same story. So, I think the key to this is going to be defining these different words. So we have a few really important terms. We have gas planet, usually known as a gas giant. And then we have ice giants, which we'll get to, Neptune and Uranus in our system, and then brown dwarfs. And the definitions for these objects are somewhat overlapping, and I think that's important, although it drives the astronomers nuts because they can't fit these things into bins. And you might say that it doesn't, why is it so important to put things into bins? And the trick is that without some constraints on an idea, it's difficult to handle it and to manipulate one idea versus another. And this is something that scientists spend there's no end to how definite we can bin things, especially when you get into the highly mathematical landscapes and information theory and trying to actually discern what one object is doing with respect to another, because it's very easy to slip down into this pit where you find things are so interconnected that it's very difficult to say anything about one particular region without considering the next. And this is especially apparent right now in fundamental physics. The Nobel Prize this year went to a group of scientists we spoke about, I believe, very briefly, but they worked on the idea of quantum entanglement, which is a demonstration of this idea that these objects, in this case atoms, are able to influence one another from very far distances very quickly, if not instantaneously. And so the question of dividing up where one object ends and one begins is no small task. But we'll do our best. So a gas giant is any giant planet that is mainly composed of hydrogen and helium. And in our case, this is Jupiter and Saturn. The ice giants, on the other hand, are primarily composed of things heavier than hydrogen and helium. So they're these more complex molecules, more complex elements, and also more molecular involvement. So we start to see interesting chemistry in their atmospheres. And the two that we have, of course, are Uranus and Neptune, like I mentioned. Now, brown dwarfs are interesting because they have the same composition as gas giants, but they're a bit larger. There's also some debate about whether they form in a totally different way, and so we're going to play with those two definitions. I'd ask you if you have questions about that, but I want to elaborate a bit further. What's interesting is that a star is also of the same composition, but we think of the material in the star, the hydrogen, as being in this plasmatic state, which is really a phase of matter that we have extraordinary difficult study, where it's very difficult to study in the laboratory. It's very hot. It's very difficult to confine it. And so stars exist in this very difficult to understand state where they're capable of conducting. The material is conductive. It's very hot, and it's generally held together by gravity and fuses hydrogen. So the brown dwarfs don't fuse hydrogen, although they do some fusion. And for a long time, people were drawing the line between stars and planets, brown dwarfs, by saying that only stars could undergo fusion. It doesn't seem to be the case. They're finding that some of these brown dwarfs are capable of fusion, just not of basic hydrogen, which is very interesting. So the more we learn about these, the more that they actually seem to be quite similar. So again, these are our criteria that I want you to keep in mind as we move through this week's discussion. Giants and stars and brown dwarfs composed of hydrogen and helium. The brown dwarf is particularly large, and there's an arbitrary cutoff set at around 13 Jupiter masses. And then the ice giants are more complex, and we'll deal with them next time. All right, so we don't have any brown dwarfs in our solar system, but we can see some in close proximity. And generally what we do when we classify any object in the sky that is luminous, that's giving off light, and brown dwarfs do give off light, is we compare their brightness versus their temperature. And we find that brown dwarfs tend towards the cooler side of the spectrum over here, where they're also quite dim. So we're going to find them in the MLT. There's actually a Y class as well. And they don't undergo this stable hydrogen fusion, and they cool down over time. And they pass through these spectral types at the tail as they cool. So to the naked eye, we can't really see the glow of a brown dwarf. Most of their radiation is given off in the infrared. This is just sort of their warm body radiation. And all of us give off infrared radiation too. Another thing, the brown dwarfs seem to, and we'll look at a diagram of this later, but they have a convective process which is quite stable, whereas in the more evolved, the smaller planets like Jupiter, for instance, you're going to see some layering effects where there's different motions of the different layers as you go down by depths. This isn't so much seen with brown dwarfs. Okay, so our nearest one's about 6.5 light years away. This is in the Lumen 16 system, which involves a couple binary brown dwarfs, which is also interesting because stars always form in binaries, and we often see brown dwarfs forming or found in binary systems as well. So again, people are trying to find signatures that indicate something is definitely a brown dwarf versus a planet. This is tricky because there seems to be a lot of planets that are also uncoupled from star systems. And it's thought these are called rogue planets. There might be gazillions of them in our own galaxy, and it's thought that these planets were perhaps left over from a solar system formation somewhere. They were ejected, maybe they bumped into somebody and were thrown out. And these are very difficult to track and pin down, these rogue planets, because you can only really see a planet when A, it's huge, B, it's close to a star, and C, it's aligned with us such that we can see it pass before that star. So rogue planets, smaller brown dwarfs are going to be almost impossible to see. And so our data set is really biased towards those that are large. But one thing that they have found, which is quite interesting, is that lithium, the presence of lithium, might actually be a good sign. There's this process where the temperature in these is just low enough so that it doesn't actually react with lithium and leaves it left over. Whereas in a star that was a little bit hotter, it would actually end up fusing that lithium with a proton. And so you don't see the buildup of lithium. Now, it's not a perfect rule. There are traces of lithium in very young stars, but those are perhaps easy to identify by their color, which is quite a bit different. They're very hot. So we can also see a little bit of lithium in heavier stars like our sun, but they don't mix, and they're easy to discern in the outer regions, in the limb of the star. So let's look at the cross-section of these, and I'm going to come back to this a little bit later. But what you can see here is that the majority of these bodies, like we said already, are composed of hydrogen. There's also helium present as well. But the hydrogen is thought to exist in a metallic form, which is interesting because it gives it the same conductive properties as a plasma. So we would expect to see much the same thing as we would in a star. It's just that this state happens to be not entirely due to heat, but due to pressure. So when you take gas, right, like we would have historically called Jupiter a gas giant, you take it and squeeze it, you end up with something closer to a liquid. If you squeeze it even harder, you end up with something that has to layer in a particularly densely packed fashion. And the best way to pull that off is with a lattice that gives you this metallic form. Metallic hydrogen is a strange concept because we don't have access to these pressures on Earth, and it's not so easy to replicate the situation where you could study metallic hydrogen. So it's almost a hypothetical form. However, it's the only thing that makes sense in terms of what the actual structure of these hydrogens happens to be. So, one thing that pops out is that the brown dwarfs versus Jupiter have a much greater preponderance of this metallic hydrogen and less of something approximating a hydrogen atmosphere. There's not really much gas phase hydrogen in the brown dwarfs, and that's probably because they're bigger, right? You've basically just extended that portion. Again, we're talking about objects that are like 13 times the size of Jupiter all the way up to like 80 times the size of Jupiter, at which point they would be turning into a star. And we're going to talk about the other two. What's interesting is Saturn seems to be maybe even a slightly more evolved version of this, because Saturn has a similar composition, but it has an even larger layer of molecular hydrogen, which gives it all of the interesting atmospheric properties that we'll talk about. Lots of different weather and so forth. So, yeah, like I said, over here we have a red dwarf, which is a kind of star, fully convective zones where there's continual churning and homogenization of the material in them. Brown dwarfs are somewhat in between. And then by the time we get down to Jupiter, we don't see a lot of this convection. There's really just this layered motion of the atmospheric structures across one another. So that's something to keep in mind as well. And I think that it's valuable to start to imagine these bodies on a continuum that suggests an evolution, because it's certainly possible that in addition to these objects forming along similar timelines in situ, in place in a solar system, that they could be moving down those lines, right? Stars evolve. Planets seem to evolve as well. Our own planet seems to have evolved. And so thinking about some planet like Saturn, or excuse me, or maybe even Uranus or Neptune, having perhaps spent some time in its deep history looking a lot more like a Jupiter, I think is a reasonable approach. And helps us understand, I think, better what these bodies actually are and how actually similar they are. Maybe they had different upbringings, or maybe their bones were different, but there's an evolutionary process here, and all planets seem to evolve, especially given enough time. Stars evolve, all these bodies evolve. You know, one thing that's really interesting is brown dwarfs are all about the same radius as Jupiter, despite how massive they may or may not be. And that radius really only tends to vary over like 10 to 15% for the entire range of masses between 13 and 80 Jupiter masses. So they can cram a lot of material and a lot of pressure into these bodies at the upper end of their mass spectrum. And so you're basically stuck looking for gravitational effects with these. And sometimes they don't have obvious orbiting bodies, right? It's again, seeing an orbiting body around a star is extremely difficult. It's even more because you can only see the shadow. With something like a brown dwarf, your chances of seeing a shadow go down significantly. Oop. So a lot of debate about the ways we can classify them, like I said. So one way to classify them, other than just by their mass, is by the way that they formed. And people are trying this on as an alternative way of classifying brown dwarfs versus planets. And the idea is that with something like a star, you have a complete collapse of a molecular cloud that leads to its formation and perhaps the nucleation of a new planetary system. Whereas in a brown dwarf, you might have a similar thing where you also get the start of stars, which would perhaps form binary systems, but maybe they kick that planet out before it can grab more of the material and actually make a star out of itself. So maybe they're sort of ejected from the system. Planets, on the other hand, are thought to accrete in place, and this reasoning has a lot to do with the timetables upon which they appear. It's thought that planets actually form extremely fast, which I will be curious if that model holds up over time, because the timelines that we have for the formation of planets are on the orders of millions of years, which is absolutely crazy to imagine if you think about, our own floor of our ocean is only 200 million years, and that's the timeline we have to form a number of these gas planets and dwarfs, which is very strange and interesting. What else can we say about these guys? Yeah, it's just that people have been really, really fighting back against this 13 mass idea. The limits changed a lot, even in the last 10 years. They've bumped it down from 80 to 60 as the upper limit of that, because they're starting to see stars that form above the 60 limit. So I think that anything that we could do to understand the difference between dwarfs, brown dwarfs, and gas planets will be interesting. The formation idea is probably the best idea that's out there, because the mass limits seem to be changing the more that we observe new bodies out there. So brown dwarfs, when we see them forming, which isn't very often, I think there's one known proto-brown dwarf out there. They're usually, in general, we'd imagine them to be surrounded by protoplanetary disks as well. And these may or may not lead to planets, but there's reason to believe that they do. So we do see disks around brown dwarfs, and these are stable systems that are already formed. like I said, there's only one forming brown dwarf that we're aware of. It's thought there's gazillions of them. We're just not able to see them yet. What's interesting is that when we do find planets around a brown dwarf system, they're very close to the sun, and they're thought to have extremely strong tidal forces that are yanking them about. And so we would imagine that those are probably the rocky type planets, since they're so close. Most of their atmospheres would have been cooked off. And there's, we're going to talk about the atmosphere cooking here in a minute as well. There's also super Jupiter ones, enormous brown dwarfs, and very cold, tiny brown dwarfs. Planets, the planets are almost always thought to be depleted of water since they're so close around these brown dwarf systems, so we probably won't find any life on them. What else can we say here? There's another class of even smaller ones, which are below 13 Jupiter masses, but we have difficulty classifying them as planets because they don't have a star system associated with them. This puts them in the strange world of rogue planets, despite the fact that they have very similar composition to stars and dwarfs, brown dwarfs. What about water? So some of these brown dwarfs actually do seem to promote chemistry that would lend itself towards water. There's an interesting reaction that goes on where in these dwarfs, there's always some sort of chemical equilibrium established between carbon monoxide and methane. And we can learn a lot about the composition of the planet depending on the tilt of that reaction towards one way or the other, because what happens is carbon monoxide reacts with hydrogen molecules and it forms this hydroxyl radical, which can then go on and grab more hydrogens and make water. But in the other direction, the methane reacts with the hydroxyl and forms carbon monoxide. And so depending on the temperature of the star, it's going to shift more towards one of these worlds versus the other. And we're, of course, very interested in the ones that tilt towards the water, which happens at the cooler end of the spectrum. And that sort of makes sense. And I think that can actually teach us a bit about the evolution of our icy giants, because they have a significant amount of water in them, and they appear to be further down the evolutionary chain, which is interesting. So we are seeing water in some of these, and we can find molecular water in the atmosphere of certain brown dwarfs. How many of them are there? There's a lot of them. So this is a representation of about 60 light years around us. And the estimate is that there's something like anywhere between 25 and 100 billion brown dwarfs in our galaxy. And this is, to be compared to about 100 to 400 billion stars. So we're aware of perhaps one brown dwarf for every 4 stars. It might be a lot larger. Again, they're very difficult to detect. Okay, so this brings us back to our gas giants, which we can think of as a special case of the same body that's too small to undergo even fusion in any kind of fusion whatsoever. Both of our gas giants have this same composition, molecular hydrogen surrounded by a layer of, or I guess it's compressed molecular hydrogen, which makes this body of metallic hydrogen. And oftentimes we think there's a rocky core inside, and we can gauge this by the density we get from the radius and the gravitational mass that we can deduce. The cores of these things are relatively poorly understood, especially when it comes to our own bodies in our solar system. Again, we can make density estimates. That's the best that we can hope for. It's very difficult to penetrate the thick metallic hydrogen mantles of these bodies and really get echoes like we did with our rocky planets. You can't land on the surface of Jupiter because it doesn't have a surface in the same way that we think about a rocky surface on a planet like our own. It just has this extraordinarily high pressure hydrogen, which would crush anything very quickly before it got very deep. And it's very difficult to assay anything acoustic in that environment as well. So you're not going to get those really nice seismic maps. But we do think that the cores are very hot and that there's the potential for rocky cores as well, which is fascinating. Especially when you talk about the processes that could lead to the densities of a planet like we have today. I mean, Earth is extremely dense compared to one of these gas giants. And compared to the sun even. It's very, very dense. And so it's interesting to think about the role that the evolution of planets could play on the formation of something rocky like our own world. Perhaps it had a giant envelope when it formed originally too that was blown away because it was too close to the sun. And this helped it crush down all of that material into a little core that left a rock behind, which is a really interesting hypothesis. That's being played with right now on the edges of science, which is cool. Let's see. Actually, this term gas giant, by the way, in case you're wondering why we call them gas giants, was coined by a science fiction writer in the 1950s. Yeah. So it's stuck for whatever reason, but they're not gas. So maybe if you learn one piece of trivia today, you can tell your friends the gas giants are not made out of gas, which is very, very interesting. All right. Well, we'll skip that. Okay, so when we look out into the galaxy in general, we can start to group gas giants. I will keep calling them gas giants because I think giant planet is confusing. There's these giant Earth-like worlds, right, that are out there that don't necessarily bear resemblance to these. But I'm talking about the planets that are primarily made out of hydrogen and helium. These gas giants can be binned into 5 different phases, right? And they all fall on a temperature spectrum. So over here we have, let's see, let me get oriented here. The hotter gas giants are going to be over here on your right. And the chemistry of each one of these is really quite distinct and interesting. So the first very cool type of gas planet is called an ammonia cloud gas giant. This is type 1. And so this is a place where the condensation reactions appropriate to the formation of ammonia are thermodynamically favorable because it's cold enough for these, if you really think about some of these reactions essentially being just what you would see in the morning when you find it's gotten quite cold and the water vapor has condensed on your windshield or something like this or on your window. It's a very analogous process that you can think of in terms of the appearance of chemistry in cooling worlds. You have a lot of these combinations which are possible only when the molecules slow down enough to interact with one another, which is essentially what it means to cool down. So then putting a little more heat into our system, so perhaps a less evolved world would have these water clouds in type 2. Still, the atmosphere is mainly hydrogen and hydrogen-rich molecules, and a lot of methane. But you get the appearance of water clouds, which are more reflective than ammonia, and so they have a different appearance in the spectral analysis. Type 3s are cloudless. These planets kind of have this featureless blue globe look to them. This is due to the same processes that give us our blue sky. It's this particular scattering of light and absorption by methane in their atmospheres. In our solar system, these would be the Uranus and Neptune. So then we move even warmer. We get these alkali metal cloud-carrying planets. This is type 4. In this case, the carbon monoxide becomes the dominant carbon-carrying molecule. So again, even more complex molecule. And these atmospheres, they start to make us think about the molecules that we would find in something like Venus. Venus is obviously a rocky planet that has almost no atmosphere compared to these gas planets. but we're tending in that direction, which is quite interesting. Then finally, we see these really crazy planets that are quite hot and large, and they have silicate clouds. They can have iron clouds. They can have diamond rain. It's just an unbelievably hot and frightful environment on these very warm, large gas giants at the far end of the spectrum. These are class 5. Now, there's this interesting phenomena called hot Jupiters, which has been discovered recently. I've mentioned maybe once or twice before when we're talking about the formation of solar systems. And hot Jupiters are quite fascinating because they seem to be, I guess I should back it up. When we generally think about the formation of the solar system, most of the classical models have the gas giants forming at a distance from the sun so they can get these big atmospheres without dissipating. However, we're starting to see that there's actually gas giants that appear right next to the suns, and they're losing their atmospheres very quickly. We call these hot Jupiters, and it's really shaken up the thinking about the formation process because, if these gas giants had to have formed in a place that required them not to have their atmospheres blown away, how did they end up next to the sun? Did they migrate in? Are they captured from another solar system altogether? What's going on? So hot Jupiters are really fascinating, and there's been a number of those discovered, and they're quite interesting. They orbit very quickly, something less than 10 days. They make their way around the star that they're orbiting. And they're very low density, which is interesting. So they don't really have the ability to maintain their atmospheres for that long at those distances. And it really opens up the question of what they'll look like, in a few 100 million years from now. Will they be blasted down and look something like Venus? Will they migrate back out and take up a position somewhere like Jupiter or Saturn and end up carrying out the rest of their lives as a gas planet, or is it just a temporary state? Very, very interesting in these hot Jupiters. And I noticed that just this year they put in an excerpt into the solar system formation section of our textbook that mentions these hot Jupiters, which is cool. That's actually the really cool part about having an online textbook that's constantly updating, is that these theories can actually shift as the scientists learn more about them and make it its way into the textbook. We're not stuck with something that was printed 10 years ago, which I really appreciate about this book, despite some other complaints I have. Another really strange thing about hot Jupiters is they appear to have, often I think in about half the cases, they have retrograde orbits, which means that they're going the wrong way compared to everybody else in the solar systems that they occupy, which is really, really strange and fascinating. And in my mind, it tilts the scales of the formation history towards something more like a capture, where it was formed in a different system or formed on its own, and then was snapped up by a star system at whatever trajectory it came in at, and it's been stuck that way, which is really fascinating. Let's get back to Jupiter. So Jupiter is the 5th planet from the sun. It's the largest one in our solar system. And this is important because it's one of the most long-lived histories of observation that we have in astronomy. And people have been more or less noting the presence of Jupiter since prehistoric times. And in almost every single culture that I could find, Jupiter, mythologically, is treated as sort of the king of the deities, which makes a lot of sense. It's the biggest, it's the most present. Everyone gives it a different name, but it slots very similarly into everyone's mythologies. So Jupiter, the name, is obviously a Romanization of this creator, father god, Jupiter, which in Greece was Zeus. But even if we go back further than Greece, we can find it in the Babylonian texts. It's treated as the deity Marduk, which is the the supreme Babylonian deity, the creator. Same thing if we go back into the Canaanite traditions, we find that Jupiter is associated with El and Baal, and we talked about El and Baal with Venus a bit, because there's a quest in the Venus mythology from the Semitic tradition where they're descending to the underworld to have it out with this creator god, the planet, which is represented by Venus, and then disappears and is resurrected and all of this. So Jupiter is central to all of these mythologies. What else can we say? The Vedic astronomers also noted it. They called it the great teacher, or guru, which is interesting. Again, a supreme deity in all of these cultures. China had an interesting take on it. They called it the year star, which is an interesting name. And what it comes down to is that Jupiter's orbital period is about 12 years. And what this means is that every year, if you have a zodiac system with 12 signs in it, every year Jupiter is going to be in a new zodiac house, right? And so the Chinese were very much keyed into it, and I think that's why they ended up calling it the year star. So central, prominent star, it was absolutely shining bright, even next to the full moon last night. I'm sure that generally speaking, if you go out there right now, at least in the next few months, years, you'll see Jupiter very, very bright. Of course, it's making its way, and Earth is making its way much quicker. You know, we'll go around and see Jupiter again before it will come back. We'll see it 12 times, obviously, as we rotate through. So, you know, go get your look at Jupiter while it's close right now. Just like the brown dwarfs and just like so many of the other gas planets, Jupiter is primarily composed of hydrogen, helium, with this mysterious core structure which we haven't totally defined. Jupiter does give off more heat than it gets back from the sun. It gives off more radiation in the form of infrared radiation, which is quite fascinating. And we see a similar pattern for Saturn as well. It has a strange shape to it because it's spinning so fast. The equator is sort of stretched out. It forms this oblate spheroid, which you can actually see just with a regular telescope. Most of our data comes from a few different missions to Jupiter. This is an interesting graphic of all the times we've visited. And, you know, I can read you some of these, starting back with Galileo's observation of the moons with his telescope, and then Pioneer 10, which did a flyby, 11 a flyby, Voyager 1. Obviously, we can't land on these planets, and so most of what we're doing is checking them out from above at very close range. And then eventually moved down, and some of our best images have actually come from the Hubble at this point. So not a ton of data on this planet other than what we can see from the outside. It does have a really, really strong magnetosphere, which is fascinating too if we start to consider the evolutionary history of all of these planets, because we're not totally sure if the dynamics that generate this magnetosphere are the same as what we see on Earth. Again, we don't think that it has the same kind of nickel-iron core, so there must be some other stabilizing feature at the center, maybe some other exotic form of hydrogen that's able to maintain that nucleation, because we do have, while there are these potentially cells which are rotating in the in the metallic hydrogen, which give it the magnetic field, the stability often depends upon a solid core. And so it's not clear how it's able to maintain such a strong and steady magnetic field. But it's enormous. The tail of that magnetosphere reaches all the way out to Saturn, which is quite crazy, almost 5.3 astronomical units. Actually covers almost all of Saturn's orbit entirely. And gives us these very beautiful auroras from time to time as the ionosphere is interacting with the solar wind. Jupiter has a gazillion, almost, 80 known moons, and a great many asteroids which are chasing it. And we talked about these Trojan regions related to L2 last time. And Jupiter has a huge cache of those. I think I have an image of that in a second. One thing that's really interesting about the generation of these auroras, and also about the presence of radio signals coming from, this was something that was really a question when I was younger, was why is Jupiter giving off these intense radio pulses? And they discovered, I want to tell you this story, it's quite interesting. They discovered that the volcanoes on Io, which is one of the moons of Jupiter, emits this sulfur dioxide gas, and it ends up sort of orbiting the moon as it's spewed out. And what happens is that gas interacts with Jupiter's magnetosphere, and it produces these sulfur and oxygen ions. And what they do is they make a little plasma sheet around Jupiter's equatorial plane. And what's interesting is that the rotating ionosphere is capable of acting much like an antenna on Earth and resonating in a fashion that gives off radio signals. And so this is a really interesting, unique resonance between the emissions of one of its moons and the planet's magnetosphere itself. Yeah. Oh, yeah. My little. Thank you for pointing that out. My machine is not happy. I need a new one of these adapters. Let's try to. All right. So what's kind of interesting about this figure is that you can see some of the moons. And we're going to do the moons in particular. We're going to get more into the moons and rings of these planets next week. We have an entire week devoted to that. But some of these moons rival the size of the Earth, which is really fascinating. Saturn's moon, Titan, is quite enormous, but Jupiter has several moons that give our own planet a run for its money. It also has a number of smaller satellites, including groups which orbit in different directions. So the prograde rotate with the rotation of the planet. The retrograde satellites orbit the opposite way, which again makes us think of capture and that these retrograde groups may have joined at a later time or been the result of some other interaction which we're not totally aware of. These are the Trojans, which I think are extremely beautiful. I wanted to show this to you. This follows the same pattern we talked about with Lagrange points previously, which is that there's these stable gravitational resonant points that bodies can essentially fall into and orbit on their own. And so Jupiter really controls the motion of these bodies. It really stabilizes them and keeps them in place between the Sun and Jupiter's system. And this is overlapping with and part of this asteroid belt. So you can see the asteroid belt in there just beyond Mars. But you also have these Trojan groups, which are given different names. There's a leading group called the Greeks and a trailing group called the Trojans. And just a great many bodies. And what's really quite fascinating is that Saturn, while it's also quite a large gas giant, doesn't have any of these Trojans at all, not a single one, which is very, very interesting. And people have put themselves to the task of understanding this. The thought is that perhaps Jupiter has such strong Lagranges that it can just pull in all of Saturn's Trojans as soon as it spawns one. So Saturn does have Lagrange points, but because Saturn and Jupiter are in some sort of orbital resonance with one another that's consistent, Jupiter is always able to swoop in with its Trojans and scoop up any of Saturn's. Jupiter is interesting because it's the only planet whose barycenter is outside of the Sun. What does that mean? It means it orbits a place that is not inside of the Sun. So Jupiter is sort of an exception. It's outside of the heliocentric universe. It could be said that the Sun actually orbits Jupiter to some extent as well, even though that point is actually only a few, well, not a few. I think that it's It's something like 7% of the sun's radius outside of the sun. So just outside of the sun is the point that Jupiter rotates. But it goes very, very fast compared to the others. So Jupiter's going around once every 12 years. Saturn's going to take something like close to 30 years to go around, which is really interesting because it means that the way that we view Saturn, the angle that we get on it is very dependent on where it is in its rotation, whether we can see these rings or not, and how bright it is really is something that's quite dependent on this long orbital period, and so we don't get quite the same view on it for 30 years, which is interesting. Now, if we compare the two of them, there's some interesting differences. So Saturn also has mostly hydrogen, but it has ices of ammonia as well. But Jupiter seems to be mostly helium and hydrogen. The magnetic field also of Jupiter is much, much stronger than Saturn, something like 20 times that. And Jupiter is much more dense than Saturn also. So what's interesting is that Jupiter still has a fair amount of mass to it. It makes us actually think that Jupiter has a rocky core. Well, we're not so sure about, sorry, did I say Jupiter? Saturn has a rocky core, while Jupiter doesn't necessarily give off the same density readouts that would allow us to make that conclusion. Now, Saturn has this like pale yellow color. This comes from ammonia crystals in the upper atmosphere. There's also a pretty significant electrical current that flows in that metallic hydrogen layer, which we think is responsible for the generation of the magnetic field, much like Jupiter. But it also has that, it potentially has the ability to stabilize it with something like a rocky core. Again, Saturn, just like Jupiter, it gives off more radiation than it receives, about 2.5 times as much, which is fascinating. It's actually glowing quite well. Saturn has a really interesting polar feature too, which caused a number of discussions when it was really well imaged by the Cassini probes, although it was noted before that. It forms this actual stable hexagon feature, which you see over here on the left. And a number of groups went off to try to explain this. It was very mysterious. But it turned out to be a simple matter of rotational fluid dynamics. So a couple of groups, I showed a picture of one of their experiments over here. They basically set up a rotating vat of water. And they found that as they stirred this water, that these regions of air would form in the center portion. And that depending on fine-tuning, they would have different bands that were stirring the water at different heights along the column. And depending on the speeds that they tuned those rotations to, they could actually generate hexagonal structures. Here's a picture of their little mixing vat. This is a different group. And they were able to essentially generate these very similar hexagonal currents, which is quite fascinating. Which is cool. It's one of the only laboratory type experiments that I'm aware of regarding the creation of astronomical features on Earth. And I think it would be, this would be a really cool branch of science to develop that we don't see a lot of, would be people replicating astrophysical processes on Earth, because they're so hard to study directly, especially stars. Like, all we can say about stars is what we can see back from the light. And so the ability to create model systems on Earth is a really fertile ground for development of new science. Saturn's orbits are very strange. Some of them are completely oblique. There's whole systems of bodies that are orbiting retrograde, prograde, at tilted angles. And so, again, we're imagining that these might indicate capture events. Particularly, we would think that as a body had been orbiting for longer and longer, that it'll stabilize and actually fall into resonance with the other rotating bodies, and eventually you get a disk. But it doesn't seem like Saturn has reached that stage yet, which is quite fascinating. So As we look at Saturn, it really changes depending on the time of year and the time of Saturn's year. We can see everything from no disk to a perfectly head-on disk, which is really fascinating. This is, how long is this taken over? I don't think I wrote it down, but this image was compiled, I think, over at least a decade of different observations of Saturn in the same point when Earth moved past it. So Saturn does take about 29 and a half years for it to complete an entire circuit. It's best seen when it's at or near opposition, and that's the point where the planet is most illuminated by the sun with regard to the Earth. This is when it's kind of opposite us, so it's getting the most sunlight, and we can see it the best. Let's see here. Ooh, storms, weather on these planets. So especially Saturn seems to have very transient weather systems, unlike Jupiter. So for a long time, we thought that this spot on Jupiter was a stable feature, like it would be there forever. But our observational history of that spot is only about 300 years old, and it actually seems to be dissipating. I think it's down to half the size that it was just at the beginning of its observational history. Saturn forms these very transient storms that appear and disappear. Here's one of them you can see, which is really quite beautiful. And this is thought to have a lot to do with how the different layers are less dense. There's a lot more motion. There's more degrees of freedom for the molecules in their upper atmosphere, and they're able to be subject to the slightest perturbations in temperature and pressure, which result in these massive storm systems, which is really something. So in a sense, Saturn seems to be a little bit further down the evolutionary pipeline in terms of getting closer to something like an ice giant, which is going to have more complex molecules, which is even closer to something like, making a giant leap, of course, even closer to something like Venus, which has very complex atmospheric chemistry, and Earth, also very complex atmospheric chemistry. So I think that I want to spend the last portion of the class really comparing, really thinking about these gas giants as failed stars, which I think is an interesting conception. So there's this, and I have a picture here of Jupiter taken in the infrared, which is a very compelling picture. It seems to evince the same qualities as a star, actually. And I think that by considering the gas giants on this continuum, we get closer to making sense of the formation stories. So, like I said, Jupiter is believed to be the oldest planet in the solar system. We can't actually date Jupiter, right? We don't have any rocks to do that by. But just in terms of its evolutionary process, the fact that it has very simple molecules, not even molecules, but elements that are not conjugated in any interesting ways, makes us think that it's older. It really seems to be closest to a star versus these more evolved planets which have worked out different heterogeneities and are able to start to develop weather and things like that. The weather system where I was going with that is the eye on Jupiter actually appears to be quite transient and will probably be gone at some point soon. And so the stability of the atmosphere is a lot stronger, but in some sense it's more primordial as well. It's thought that the original hypothesis is that Jupiter formed at or beyond the snow line, which is this distance from the sun where it's sufficiently cold for molecules to condense, like water. And that the planet began with this solid core and then accumulated all of this gaseous atmosphere. And so it must have formed before the solar nebula was totally spread out, where there was a lot of clumping of materials. And then, it kept accreting this gaseous matter until it was like something like 20 times the size of the Earth. And then once it was 50 times the size of the Earth, it created an actual window in that solar disk, in that nebula that was forming planets. It made a little room for itself, where it was able to actually take up other bodies and begin to act on its own. So at that point, it's thought that there may have been some migration events. And Saturn also would have migrated too. So this is the trick. How do you explain the presence of all of that material being so far away from the interior of a accretion disk, which is forming a planetary system? Again, the model for the formation of solar systems right now comes down to all of this material coming in like a figure skater and gravitationally collapsing, and you form a star system. The problem is that some of these planets, these gas planets, are so enormous that it's difficult to reconcile why they would be so far away from the interior. And we do find them forming near the interior in some places. These were these hot Neptunes, these hot Jupiters that I was talking about. And so people have been really entertaining these migration ideas, both for Saturn and for Jupiter. And this is kind of the state of the discussion right now, is what timetables would allow something to have developed in this cold zone where this condensation reactions can appear, but it also needs to have followed a model where the majority of the material can be close to the center. And so it's thought that there was some transition that was occurring. And this is actually competing with other ideas that suggest that perhaps Jupiter and other gas planets form as the result of an interaction between two different star systems. And it's not totally clear the mechanism of that. What I mean is perhaps Jupiter resulted from a collision between two stars where a big piece of material was broken off. Alternatively, perhaps Jupiter was grabbed from another star system, or it formed like a star in place. It collapsed with its own accretion disk and everything, and then was grabbed up by our own star, which is a really fascinating idea too. But in any case, the stability of those orbits, as they're understood in the early solar system, is such that it must have happened very quickly, like on the order of a few 100 million years. And so it's not entirely clear how we resolve the differences in these planets. It's becoming increasingly difficult to explain the planets as having formed exactly where they're located at. They must have gone through some journey. And again, all of these planets fit in a really nice, yet slightly confusing way into a continuum that suggests some overlap in their history, some overlap in the way that they're formed, maybe some differences in their nature versus nurture. They were formed from different elements. Maybe they spent different times in different temperate zones of a solar system. Maybe they came from other solar systems altogether. But I think it's a really wise thing to start thinking about the processes that would lead to the formation of different gas planets that we see out there, because it's certainly possible that they could spend time as different types of gas giants, right? Especially as our timetables expand for all of these processes. I think that the reason that astronomers haven't treated the evolution of planets on the same continuum as the evolution of stars is because the timetables were initially so small. It was originally believed that these planetary systems formed in the matter of millions of years. And why did they think that? Again, all of our dating techniques can only concern rock, and they concern rock. These are the radiometric processes. They concern rock, and they concern rock that they can only tell us when that rock was last completely melted, right, and incorporating new radioactive elements. And so if we're left with the impression that because of this, our solar system has only been around for 4.5 billion years, and because of the evolution of some of our rocky planets, we think that they've basically been the same for most of that time. Some of their surface features may have changed, their atmospheres may have evolved a little bit, but there's not a lot of time for these formation processes to happen. Now, if it turns out that the solar system is much older than we're giving it credit for right now, then that's going to open up the horizon for embellishing the stories of how these planets could have actually spent time in different solar systems, perhaps, spent time in different regions of their own solar system, and maybe fitting each one of these bodies onto a more strict evolutionary timeline will start to make sense. But as it stands right now, there's very little time since this, there's a very little space between 4.5 billion years and 4 billion years or so for all of these planets to have taken shape and fit nicely into the forms that we recognize them in today. And so I guess we're going to finish a little bit early. I think that's a really good place to stop, because next class we're going to talk about the ice giants, and I think that they also fit into that continuum in a really interesting way, because they have some of the most complex chemistry of any of the giant planets. Questions? Yeah. Oh, I believe it's due on December 3rd. It's a Saturday. Is it the 3rd? Okay, cool. Yeah. Anybody else? All right. Have a good week, guys. We'll see you Thursday.